Good evening, all. See, this is the today is my last lecture of this trace metal analysis as far as the analytical portion is concerned. And today we are going to speak about only the one single analytical technique, that is the neutron activation analysis. See, this particular analysis is different from the than compared to the other ones, because here we introduce we make the nuclei unstable, and then based on that, having an instability in the nucleus, there are some radiations are coming out of the system, and that we will detect it, and that we will see how we are exploiting that situations to determine the concentration of the various elements and how it is different from the compared to the other analytical techniques. So let's see again before going for the lecture. This lectures, let's have a recap. See, we had started with our journey with the analytical terminologies, and this analytical terminologies, many people were wondering why we had to start with such an elementary thing. But since whenever there's a gathering of a multidisciplinary peoples, they always beneficial to have to know the various terms involved in the analytical chemistry. So that's how this analytical terminology portion was included in these lectures, in this particular 6 lecture course. And in this we have seen the samples. What is the meaning of the samples and the matrix? So that basically sample is a combination of both analyte and the matrix. So except whatever the element of my interest is, that except my element of interest, everything we consider as a matrix. Then we also gone through this terminology of a contaminant. See, contaminant may be analyte also. Anything unintentionally added to the sample. See, whatever, for example, if I am doing the cadmium in any alloy samples, and somehow because of either due to sample storage or by during the process of analysis or due to the processing, because of any reason there is any additions of the lead in that alloy, that is called as a contaminant. So lead is also a contaminant. So anything which is unintentionally added into the sample is termed as a contaminant. Of course, we are here targeting on the analyte only. Then we have seen the definition of the what is mean by the primary standard, secondary standard, and then see we have seen also the sensitivity of the instrument. Sensitivity of the instrument is nothing but the slope of the calibration curve. And then we are also seen that the internal quality assurance and the external quality assurance. Actually, what is the meaning of the internal quality of assurance and the external quality assurance? And during this course of lectures, I also told you the importance of the external quality assurance, actually, external QA/QC, because external QA/QC, if it is conducted by any authorized agency, see, in each country, there is one authorized agency is there, and that will carry out the external QA/QC. If it has been conducted by that external agency, you had been termed as a, you had been given as this qualification of a 17 that your lab is accredited as per the 17025/2017, because this is this 17025 is basically a set of instructions are there how to perform the analysis and how to manage your laboratories are there. So both there is the administrative as well as the what kind of procedures, discipline in the laboratories, all these things has been very meticulously been framed in the one particular rule book, that is there's a 17025, and once it has been conducted by that external agency, your lab is known as the accredited lab, and then your results will be valid in all kind of law enforcement agencies if you go to the any court and all those things. So then your results are your results are reliable, and they will be not be questioned by the law of court. And then we also see the importance of the traceability. See, traceability means all this kind of whatever this measurement has been done, whether by the chemist or by the electrochemistry or by anybody else. So there are 7 assay units are there, and as far as the analytical chemistry is concerned, we are 2 assay unit either in a mass in kilograms or in moles. So whatever our results are there, so it has to be traceable to those numbers, that is either mass or kg. Then only your results are reliable actually. Then we have seen that the various kind of analytical techniques are there. So what we had come across, there are 3 kind of analytical techniques are there. One is the gravimetry techniques. Gravimetry techniques are supposed to be considered as absolute methods. What basically they are absolute method, and under the absolute method category, gravimetry is one of them. And what is the advantage of, what is the major advantage of this absolute method is that their relative standard deviation are less than 1%. Then we have seen these relative methods and comparative methods. So relative methods generally those methods where we draw a calibration curve by using a standard solutions, like we have seen in case of a UV visible spectrophotometers, ICP-OES, FES, JFAS, and ICP-OES. So all those things, these are the techniques which comes under the relative methods, because whatever the measurement we are carrying out, they are based on they are related to our standard samples. So whatever the concentration we are arriving at finally, they are based on the calibration curve. Then we have seen some of these comparative methods. See, comparative methods are those methods where comparative methods also needs a calibration curve, but these calibration curves are different than the way we prepare the calibration curve. They are different from the relative methods. In this case, comparative methods, matrix matching standard is compulsory. As I given you, for example, if I am doing the analysis of arsenic in any vegetation samples, then I will prepare a calibration curve using the arsenic in the vegetation samples only. And the methods are like X-rays, OES, optical emission spectroscopy. These are the methods. And then today, whatever we are going to discuss, neutron activation analysis, that also comes under the comparative methods. So there also we need a matrix matching standards is must to have a meaningful measurements. Then we have seen some part of the solution and the stoichiometry. While discussing the solution and stoichiometry, basically stoichiometry means what is the meaning of whatever the alphabets given in the parenthesis that denote the physical state of the particular compound or molecules, and then coefficient used in the equations are basically to balance the equations, because both the side of the equation the same number of atoms. Then we had gone from the evaluation of the analytical chemistry. We start with the gravimetry analysis, and there is a problem which comes under the gravimetry analysis, because the gravimetry analysis is only possible when we have a large quantity of analyte. That means that we are in a percentage levels. And then it is also possible, there are many elements. We do not know the chemistry and not easily get precipitated out. So that's why the problem which is associated with the gravimetry analysis, although we go to the gravimetry comes under the category of the absolute methods and having a RSD of less than 1%, but there are errors are there. So those shortcomings have been removed by using the volumetric analysis, in which the acid-base titration, redox titrations are there. And then comes whatever the issues faced in the volumetric analysis has been further resolved by using the calorimetric analysis. In case of calorimetric analysis, the element of analysis has been done the study based on the color developed by that particular element. Then we have discussed the importance of the sampling, and again, this is a very important point. Again, I'm telling the same thing only, because see, if you had conducted any error while doing the sampling, See, whatever best results, whatever best lab, whatever best analyst you are going to end up with the wrong results, or the results will not be very near to the actual values, because we are committing a mistake at the grassroots level itself. See, basically, the sampling means sample has to be chosen, which should be, representative of the, because it is not always possible to analyze the whole samples. So you just take a allocate or a part of the samples and do the analysis. So that you allocate or the small amount part of the sample should be representative of that whole load. Similarly, we have seen this. Uh, that particularly represent the whole load. And similarly, we have seen in case of the water samples, and suppose you are going to take a sample from the rivers, and see whenever the sample has been taken for the river, so basically the concentration of that element you are going to give up for the that river, the water, the inlet in that river waters. But you are done most of the time, you do the spot sampling. Spot sampling means you just go there, grab the samples, and then come to the laboratory. But actually, that will not give a correct result. That is the value at that place only, at that particular time only. And then, if you are aware, or if you have some knowledge about the environment, that the concentration of the metals, the analyte will vary with the depth of the with the water table also. So that is basically whatever the sample you have taken it, that represent the surface water only. Okay, so it does not represent the water which is there existing through from the with the depth of the river or whatever the water body the sample you have taken. So one has to be very chosen while taking the sample, and same thing is true even for the synthetic chemist also. The synthetic chemist, if you have done the synthesis of about say 10 gram of the sample or 1 gram of the sample, to analyst you are just providing a milligram or 100 milligram of the sample only. So whatever the sample you are given to us, it must be representative, and that should be homogeneous. That, see, this care has to be taken by the analyst or by the person who had done the synthesis. Because if you are giving me the wrong samples, or you are taking, suppose there are some hot spots are there or some hot particles are there, and you have given me that those particles only, so definitely you are going to lead with the concentration of the element will be at an elevated level. And suppose if you have chosen something which is on the negative side of the side, then you will get a value less value whatever you are supposed to be. Then we have seen the importance of this sample storage. How important is sample storage? Because it's not possible to do the analysis on the spot. So you have to collect the samples and bring the sample to the laboratory. So during this process of transportation and as well as during the storage, because there is a time lag between the analysis and then the sample received in the laboratory. So during this process also, you should not add, or you should not lose any information of the analyte, and this information lost because of the adsorption of your analyte on the walls of the container. Sometime in the gas sample, it will react with the atmosphere, and if you had not kept your sample properly, for example, it had not been isolated from the external environment, then you will get definitely the contamination from the atmosphere of your lab or whatever, wherever you are store your samples. Then we have seen the importance of this sample digestion, and the sample digestion is again very crucial and critical part, because during the sample digestion you have to make very sure that you had completely taken out your analyte out of that matrix. Okay, and then you have to see that whatever any matrix interference are there or any other interference are there, that has been completely avoided. And during the sample digestion, whatever the reagent has been used, they should not contaminate your samples. And these things of sample digestions and storage are very important when we are dealing with a very, very low concentration. For example, as we say, the integration of the environmental analytical chemistry, where we generally deal with either in a ppm or a sub ppm or ppp or sub even up to the ppt level. Some of the emerging contaminant goes up to the ppt level also. So there one has to be very, very careful while choosing your way of sample digestion to bring the sample digestion has to be done to bring your analyte into the a form where you can perform the analysis. So during this process, during this step, one should not lose the information or does not add any kind of a contaminant in your samples. Then we had discussed about the separation chemistry. See, separation chemistry, we had just seen, the element of interest can be separated, or the major matrix can be separated either by using solvent extractions or ion exchange, and then, or maybe because of chromatography. So in the solvent extraction, I given the example of this removal of the uranium because when one has to carry out the analysis of the trace element or impurities in the uranium metals. So how to avoid those things? So we use the tributyl phosphate, where the major matrix, that uranium will be taken out and iron and aluminum will or the trace metals will remain in the aqueous phase only, and then one can perform the analysis without any interferences are there. Then we have seen various the anion and cation exchanges, and then do chromatography also. In chromatography, we have seen that they are basically classified based on this mobile phase and the stationary phase, and then on the basis of various kind of interaction between the analyte and the stationary phase, they will be further. There is a classifications are there. And in this process, in this particular section, we have learned about this gas chromatographies, HPLCs, and yes, I think this HPLC and gas chromatography. These are the two techniques we had seen it, and then of course this thin layer chromatography also. And there we how to evaluate these, retention factors, because basically many if you are a student or you are for this particular course also, you have to give some exams are there, so that we have learned how to evaluate the retention factors, this thing. And then in the next lecture, we had discussed about this interaction of the electromagnetic radiations with metals. So there we discussed both this atomic as well as the molecular spectroscopy. So molecular spectroscopy is a very small portion that you use your part while doing the using this spectrophotometers. And then in the atomic spectroscopy, we had seen both this flame atomic absorption spectroscopy, the graphite furnace atomic absorption spectroscopy, and in this particular section, we also seen that hydride generator. So basically, there is a three different kind of atom cells. Atom cells means where we convert our analyte into atoms that can be converted in case of by using a flame. So flame, we have seen that two different kind of flame, that is nitrous oxide acetylene when we need a temperature about 2300 degrees centigrade, and in a graphite furnace, where the temperatures, and then nitrous oxide acetylene flame where the temperature is about the 3200 or 3300 degrees centigrade are there. And similarly, we have seen that graphite furnace. So there, what is the major advantage of the graphite furnace when compared to the flame and atomic absorption spectroscopy? Whenever the quantity of the sample is very small, so generally it has been preferred to done by this graphite furnace because and this is very beneficial when we especially look for the trace element analysis in various kind of body fluids. Because generally we don't get a large volume, and then without dilutions, the study is possible when we can use this graphite furnace. And some of the element which is give in a very possible to form the hydride like selenium and arsenic, we prefer to form a this hydride generator, that's basically a quartz cells, so where the sodium borohydride and HCl is used, hydrochloric acid is used to make their hydride, and then this hydride will be atomized in the flame, and so that our detection limits will go in the PPT, PP sub PPV range. And there, we also seen that how to remove various kind of interferences in this. So in this case, we have seen the spectral interference. Spectral interference can be avoided by just taking different lines, because there are many absorbent lines are there. So I think in this case, I have given the example of aluminium. So aluminium is we can choose a different line. If suppose two very close lines are there, then better to choose a line which is doesn't having interference. Then we also seen the ionization interference. There are the certain alkali and alkaline earth metals which can easily ionize in the flame. So there is a lot of electron formations are there. Because ionize it. So how to suppress those this thing? There we use a potassium chloride solution, so we have a excess of electrons in the flame, and then they will shift the equilibrium to the atom side. So that's how we avoid this ionization interference. And then we have seen this background corrections, continuous background corrections up to 450 nanometers. So there we use the deuterium lamp, and some of the corrections can be used, for example, the Gemin corrected Gemin corrections. And these, what kind of corrections are needed, where to do those corrections? Actually, all those things are Gemin corrections or the continuous background correction. We have seen they are already inbuilt in your atmosphere, in your instrument. So once you are not getting a good calibration curve, so you can then decide that whether you will go for a whether this continuous background corrections or a Gemin corrected spectrum. So this is how we have seen, and then we discuss this ICPUS. So the major difference between these FES and GFS. Basically here in ICPUS we can use the emission line both from the atom as well as the from the ions. So that's a distinct advantage because they have temperature, because we are using a plasma. And here our analytical zone is about, say, in the range of 5,000 to 6,000 Kelvin. So at that particular temperatures, there's many elements we can be able to detect it. And since we are using a good detector having a resolution of the 9 picometers, or nowadays even the 4 picometers systems are available in market. And in this particular case, we have seen we can do both the sequential as well as the simultaneous detectors. We can use either CCD for the simultaneous ones, and then for the sequential, we have a PMT detectors are there. Then we are also discussed here about the mass spectrometry. The mass spectrometry is the major part of this, how to ionize it. See, you have to, whatever your compound there, first step is the ionize it, then ionization has to put in the mass analyzer, and the signal coming for the mass analyzer fed to the detectors. So there we have seen that, you can, there are many elements are there which having a various natural isotopic abundance are there. I think in this case, we have seen the example of this chlorine and bromine. Both with the help of mass spectrometer, we can, by knowing the ratio of the ethyl chain and this bromine and chlorine ratio, we can see that whether the one bromine atom is attached with the molecules or one chlorine atom is there. So I think we have discussed both this example of I think ethyl chloride or propyl chloride, propyl bromide, I think, if I correctly remember. Then we had discussed some of the basics about the electrochemistry. Electrochemistry, we had seen that, this basically both type of cells we had discussed that where the chemical energy is converted to electrical energy, like Daniel and a galvanic cell. And we have also seen that the electrical energy convert to chemical energy, that in case of electroplating. And then we have seen this how to connect the standard reduction potential of electrochemical reaction with the standard reduction potential and with the activity and the temperature of that particular electrochemical reactions. So that's how we define the Nernst equation. And then using the Ilkovic equation, we can have a relation between the diffusion current and the concentrations. And this electrochemical reaction, this has been signatured on the basis of the half-wave potentials. And then we have seen that how this half-wave potential very specific for all the element. And one of the distinct advantages of the electrochemical determination is that because this halfway potential for the element as well as this chemical species of that particular element are different. So it's not only possible to determine the concentration of the element, but you can also do the speciation if, by using the electrochemical reactions are there. So in this we have discussed this for classical polarography. And while discussing the classical polarography, we have seen that there is a limitations are there. So in the limitations, because of those limitations, we cannot determine the very low concentration like in case of FAS and GFAS. So to further this, the modification has been come in this electrochemicals system by introducing a both voltage sampling and introducing a good microprocessor. With the help of that, we can do this voltage sampling, and we can play with the voltage sampling as well as the current sampling. And because of those modification, the resolution go up to 0.02 volts, and the detection limit can be achieved to the ppm or ppb levels are there. And in this particular case, we have discussed the detection of the uranium in the pp range by using the adaptive stripping voltammetry, where the selective adsorptions of the uranium has been done on the chloroanionic acids. And then we are also seeing the determination of the anthracene in the glassy carbonate. In this lecture, also we discuss about some very basics about the thermal chemistry. Thermal chemistry is nothing but those reactions where we are monitoring the reactions, whatever the changes are going on with either with respect to temperature and time. So whatever these changes, thermal reactions are going on. So in this, we have seen that TG, which is basically in which there is a change in the mass as we increase, as we vary the temperatures are there. So that is called as a thermogrammetric analysis. And when we take the derivative of that mass change, it can be done with the help of derivative also. Then we have seen that both DTA and DSC. DTA is nothing but, we are measuring the delta T versus T, because in this case we are taking sample and reference, and we measure the, we are recording the delta T versus T. And while in case of a DSC, we are measuring the difference in the heat flow between the reference and the sample where this reaction is going on. And because of those, there is many informations, whether the reaction is exothermic like melting point, crystallizations, and glass transition, phase transitions, has been evaluated with the help of these techniques. And in the last lectures, we had discussed about the hyphenated techniques. In the hyphenated techniques, basically, when the two techniques had been combined, like the name says, hyphenated means two things had been combined. So we have seen the combinations of both ICP-MS, GC-MS, LC-MS, and we have also seen that MS-MS. Then we are also seeing that LCFTIR, LCFTIR NMR studies are there. So that we during this lecture, we have seen that how they have simplified our life. For example, in the analysis of the pesticide by using the GCFN MS, I think aldrin, linden, and this endosulfates. The alpha and beta both forms had been very easily not only separated but simultaneously determine also what is the concentrations are there, and with a correct fingerprinting has been identified in the samples. Similarly, with the help of LC, this LCMS, we have seen that I think we have discussed about this presence of fungi. I think there's a B1 alpha toxin actually. I think B1, G1, and B2, G2. There are the 4 different kind of toxic materials are there with, which can be determined easily by using this LC MS. So this is how up to now what we had gone through, and then in this lecture we have also seen that both arsenic and antimony speciation by using the various hybrid techniques. So there I think I had given you a reference of one review articles where the various kind of hypnotic technique had been used for determining the various species of a arsenic as well as the antimony. Now, friends, so let's start with this today lectures. And before going further, if you have any queries, then you can ask me. So definitely, I will be very happy to answer your queries. And if I do not know, that I will take the help of my other learned colleagues to give your answers. Okay. I think there is no query. So now we are going to start this today lecture. So what we will see that we will see something about the very basics about the radioactivity, because this particular technique is based on the radioactivity. And then we'll talk about a very brief about the various sources of radioactivity, and then the estimation of the stable element by radioanalytical technique. See, this is a very important word, the stable element. The element is stable, but we are using a radioanalytical technique. It means that we are going to make that element unstable, and then we are going to detect it. And then the estimation of the gamma emitting radionuclide, because we are going to introduce the gamma activity in that particular stable element. And then with the help of these gamma emissions, we are going to both quantify both qualitative and a quantitative analysis has been done for those these various stable element, trace element, what we call is a trace element, or you can call them major or minor elements. And then some of these applications. See, that's why I say that very basic of the radioactive. Why a element is unstable or radioactive? Unstable elements means here we are talking about the radioactivity, because cannot take the very basic lecture on the radioactivity. So just I introduce this and by jet ratio graph. See, in general, in most of the cases, if this neutron to this n by p ratio is 1, because then the element is considered to be a stable one. And this is a theoretical picture where we have a 1:1 n by p plots are there. But in actual, this is like this graph is coming, because whatever the predictable there, this ratio will come in this fashion. And this also, whatever the elements are there, they all are, these stable elements are there. See, element which is lying on this, which having a more number of neutrons, they generally, decay by releasing a neutrons are there. This is called basically beta minus decay. That more number of, if they are having more number of neutrons, they decay by the way beta minus decay. And if they are having more number of protons, they will be going to the beta plus decay. And in case of some of the elements, heavy elements, which having a mass number of more than 82, 82 protons are there, then the and having a more number of protons are there, they will undergo this alpha decays are there. So what is mean by the beta decay and minor? See, beta decay means one of the neutrons will be converted to the electrons, and one is happening. Okay, so what will happen in this case? So it will be that you will be shifted to the left side of the periodic tables. And when it's given the beta, because the new element will be generated, and then similarly with the beta plus decay, so what happens? You will shift it to one step of the periodic table, that new element, whatever is going to be generated. Similarly, in case of a beta alpha decay, that shift will be the two numbers. So these are the various kind of radioactive decays are there. So alpha particle, that is basically helium nucleus, which having a 4 mass number and a 2 uh, beta negatives. So that is the electron decay, has been denoted by the 0 and -1, and beta positive positron, that is 0 and 1. Whereas the gamma, that is a high energy photons are there, but it does not have any kind of a charge, and the mass numbers are there. So that's what I'm telling you. In the case of a beta decay of a neutron transfer into a proton by emission of an electron, and then accompanied by an anti-neutron, that is to balance the equations. And similarly, in case of positron emission, proton is converted into a, that is a beta plus decay, is converted into neutron by emission of a positron and with a neutrino. And this is how this the electron captures. So what is radioactivity? Radioactivity is measured as the number of disintegration that a sample of radionuclides undergoes in a certain period of time. And generally, the unit is in a curie, and 1 curie is equal to a 3.7 into 10 raised to power 10 disintegration per second. And that is this how many becquerel. This disintegration per second can be denoted by the becquerel, that is a BQ. Okay, as I told you, one becquerel is equal to 1 disintegration per second, and when you turns in terms of picocurie, so 1 becquerel is equal to 27 picocurie. So these are the units you can see in the various. Whenever you are going to denote the concentration of the radionuclide species, either it will be given in a becquerels or in a curies, or you can say in a picocurie. So this is how the general, this is basically those people who does not, because I come to know there is some mechanical engineers also there. So this is how, this is for the benefit of those people. So how to denote an radionuclides. See, this is basically atomic mass, that is 238. Okay, there is a mass number. A means mass number, and Z is the atomic number, that is 92. And then this is called a n is equal to that is a minus z values given this n values. See, this is how this radioactive decay, because it's follow the exponential curve, and this is basically the initial number of atoms, and now they will be the exponential n is equal to n0 e raised to power minus lambda t. Okay, and here is a lambda is nothing but 0.698 t half, that is this is a half life of that radioactive atom, and t is the here t is denoted in the time elapsed actually. This is the how various kind of a radioactivity existing on the earth. So see, our earth is having a both natural and a man-made radionuclides are there. As far as nature is concerned, we are having many cosmogenic radionuclides, because these cosmogenic radionuclide forms produced by interaction of the cosmic ray with the air. And in general, this in air we have a neutron flux about say 2.6 neutron per square centimeter per second, and this flux, this intensity of the flux vary with the latitude and the longitudes at the different parts of the earth. But in general, the average value is 2.6 Newton per square centimeter per second. And because of these interactions, there is a production of the helium, beryllium 7, carbon 14, and krypton 81 other. Then primordial radionuclides, since the genesis of the earth, there is many radionuclides. For example, we see the natural series of the uranium, thorium, and then uranium-235, they are actinium series, we told it. So they are the three radionuclides along with the potassium 14. So these are primordial radionuclides. They are having a very large half-life actually. That's why the written is T half is great enough related to the age of the earth. For example, potassium 40, which having half-life of 4.5 into 10 raised to power 9. I think in case of uranium is about 10 raised to power 10. I don't remember the exact the half-life of that uranium right now, but I think it's the order of 10 raised to power 10 years. Then comes the man-made radionuclides. See, man-made radionuclides started with this nuclear powers. In nuclear power, there are many our reactors are there. So we are doing this artificial fission of the uranium-238. Or most of it is uranium-238. In other cases, there are some others also involved. And then there are the nuclear weapons. There are so many atmospheric testing has been done before 1960. Before 19 up to 1960, I think most of the whatever this testing of the weapons has been done, either they are in the atmosphere or they are in the down the earth, or maybe sometime in the sea also it has been performed. Because of that also there is a lot of spread is there. And then there is a two major nuclear accident like Chernobyl and now this I think recently then the Japanese also. So they have contributed a lot for this the entire globes. The distribution of the radiant gates are there, and then nuclear medicine and research. Whatever there is a very small contribution coming from those top these two section also, that is nuclear medicine and the research are there. So these are termed as a man-made radiation. Because of these regions, there is a radioactivity are there in one or other forms are there on the earth. Now, what is the basic theme of this today lecture? That is the estimation of the gamma emitting radionuclide. See, gamma emitters, they are very high penetrating power, and therefore we need a very minimum sample preparation is required in this case. See, what we do it, we can just take a solid and liquid samples and put in a proper container. See, the container has to be fitted in such a way that it should not contaminate your instrumentation or the wherever your laboratory is there. So, a suitable container should be there. And then it can be done, detection can be done by using this high purity germanium or the sodium iodide thallium detectors are there. Nowadays, both the new generation detecting material that we termed as a lanthanum bromide, having cerium as a scintillator is that also giving a good results now results, and people are using it because having its resolution is better than compared to the sodium iodide, and it does not need liquid nitrogen as in case of a high purity germanium. So it's very easy to use it lanthanum bromide, but it's have its own issues are there. So these are the estimations of stable element by radioanalytical technique. In general, radioactivity in stable element is induced by bombarding with a proton, electrons, and a neutron. And during this lecture, we'll concentrate only on the radioactivity in element induced by neutrons only. So this particularly whenever the radioactivity is introduced in the element has been termed as the neutron activation analysis. And neutron activation is a powerful isotope specific nuclear analytical technique for simultaneous determination of elemental compositions of major, minor, and trace elements in a diverse matrix. And these techniques having very highly sensitive and a low detection limits actually can be achieved by using the neutron activation analysis. See, as the activation analysis based on the nuclear reaction for the determination of element at major to ultra trace levels. So here basically the element we are interacting with any projectile. This projectile can be of a neutron. If it is neutron, then it will be termed as a neutron activation analysis. This projectile may be of a charged particles, and these charged particles can be of a alpha particles or a protons or a deuterium beams will be there, or heavy ions like 16 oxygen, 11 boron, or 20. I think already I told you that this can be used for the qualitative and quantitative determinations. This technique can be used for both the qualitative and quantitative determination. After doing the irradiation of the sample with a neutron, and this is how this is what is happening when you irradiate your element with the neutrons. See, when the element will getting irradiated with the neutron, it will be captured by that element. A compound nucleus will be formed. And once the compound nucleus will be formed, that will be become a radioactive, and then it emits a beta particles. Once after it emit a beta particles, then they live in a atom in the excited state, and due to bring this the excited state to low, it will emit a energy that we call say gamma it will emit a gamma radiation, and these radiations we detect it and use it for the both for the qualitative and the quantitative purpose to determine the concentration of that elements. See, basically here what we are discussing about this, there's a two kind of a detections are there. This one is a prompt gamma neutron activation analysis, that is PGNA, and other is a delayed gamma neutron activation analysis. The prompt gamma neutron activation analysis, see, immediately after doing this irradiation, you can determine on the spots itself. So that's because without any delay, that will come as a prompt gamma neutron activation analysis. But sometimes it is not possible, so we bring it because so much, activity has been introduced in the samples. So what we bring it the samples after doing the radiation, we bring it to the lab and then do the determination that will be termed as a delayed gamma neutron activation analysis. And see, basically, these are the three different type of a neutron source can be utilized, can be used. Yes, well, Sai, Sai, you can put your question in the chat box. Hello. कुछ है नहीं, कुछ नहीं है ना? Okay. So these are the various type of a neutron source are there. So बस ये क्या listen come, ये साई raise hand ऐसा लिख के आता है. ये ना साई कौन सा भी है? नहीं है. Okay. Okay, so there are the three different type of neutron sources are there. So one is called they are basically laboratory based. So it can be a 250 californium source, and this is spontaneous fissions are there. Because of the spontaneous fission, you get a regular supply of the neutrons. And thus, second not means in this category itself, there's a 240 americium beryllium source are there, and then another one is a 239 plutonium beryllium source are there. And one more, this antimony beryllium source is there. So these are the four sources are there, which can, you can take these sources with the proper permission, and you can irradiate your sample there in your lab itself. But what is the problem with these sources are there, that the flux, I think flux is an issue. And here the flux is, I think, not more than 10 to the power 6 neutrons per square centimeter per second. Whereas if you are having a nuclear reactor where we have a flux about the 10 to the power 12, and so there you can get other major informations, and these fluxes are only possible when you have access of this nuclear reactors are there. So I will show you what are the fluxes in all these reactors, whatever we are having. And then some of these accelerator-based fluxes also there that will be used for the getting the neutrons and can be used for the irradiation of your sample with the neutrons. So these are the reactors, that is the Apsara, the 90. Of course, now we had decommissioned it. That's the first reactor which has been in India and it has been used for these. Basically, its major use is we have done it for this neutron activation analysis only. Then we have a Cyrus, which having a 40 megawatts of production of the power, and then it's used in natural uranium. Then Dhruva, we have 100 megawatt. And then this is we are having this BTR 9085 again is using this uranium plutonium carbide fuels. Then we have a Kamni, and then now we are having this whatever the Apsara we are having it here. We have upgraded it and it will start functioning from the 2018 onward. And so about 2 megawatts, and now it's going to become our workhorse for doing this neutron activation analysis. And these are the various fluxes. See, we are getting in this the Cyrus and Dhruva reactor, whatever about 10 to the power 13 Newton per square centimeter per second. And whereas the Apsara reactors, we are having this Apsara upgraded reactor because now there is no more Apsara reactor is existing. The Apsara upgraded reactor, we are having 6 into 10 to the power 13 Newton per square centimeter per second. So whereas in the Kamni 10 to the power 12 Newton per square centimeter per seconds. So these are the various research facilities which are existing in India for carrying out the neutron activation analysis. Apart from the sources, whatever the 4 different sources I have shown in my previous PowerPoint. So either you can have those sources at your lab, but that the flux is, I don't remember exactly the flux, but I think is of the order of 10 to the power 6 Newton per square centimeter per second. So you will not get that kind of information, which is possible when you irradiate the samples by using the flux, this flux. This particular, we are showing this, neutron energy spectrum. So basically, there are 3 different kind of neutron energies are there. There is a thermal flux, epithermal flux, and the fast flux. Then we will see that what are the utilizations when you irradiate your sample either with the thermal flux, epithermal flux, and with the fast flux. So in case of a thermal flux, basically the energy of neutrons, the thermal energy of the electron is about the average energy is 0.025 electron volt. And this basically whatever the flux is less than below 0.5 electron volt, they will comes under this thermal flux. But the average this energy is about the 0.025 eV. And in most reactor irradiation position, 90 to 95% of the neutrons that bombarded a samples are the thermal flux. So the positions in the reactor have been chosen in such a way that 90 to 95% of the neutrons that bombard the samples having the flux of having this neutrons having energy of average energy of 0.0225 eV. Then comes the epithermal fluxes. The epithermal fluxes are ranging from the 0.5 electron volt to 0.5 MeV, and they are only they are partially moderated. And generally, when we irradiate the samples, so how to avoid the thermal fluxes? So thermal fluxes can be avoided just putting your sample in this cadmium foil. So if your sample had been put in a 1 mm thick cadmium foil, so which absorb all the thermal neutron, and it will allow only to pass through this fast neutron, that is about say 0.5 eV to 2.5 MeV. And a typical unshielded reactor's irradiation position, unshielded reactor position, the epithermal neutron flux represent about 2% of the total neutron flux. And both thermals and epithermal neutron induce N gamma reactions on the target nuclei. In neutron activation technique that employ only epithermal neutron to induce N-gamma reaction by irradiating the sample, it has been termed as a epithermal neutron activation analysis. Then we have fast fluxes that have an energy of more than 0.5 MeV. And this fast neutron contributes very little to this N-gamma reactions. But instead, they induce a nuclear reaction where the ejection of one or more of the nuclear particles like protons or alpha particles or even the neutrons are prevalent. And a typical reactor irradiation position for 5% of the total flux consists of a fast neutrons. And if the activation analysis has been carried by using these fast fluxes, it has been termed as a F and AA. That is fast neutron activation analysis. So neutron activation analysis category according to the type of the emitted gamma ray measures. See, if the prompt gamma ray is measured, then it's termed as a prompt gamma neutron activation analysis. And the measurement take place during irradiations. Detectors are placed very close to the samples, compensating for much of the loss in the sensitivity due to flux. And if the delayed gamma ray is measured, is the measured radiation, then it will be termed as a delayed gamma ray neutron activation analysis (DGNA). And basically, DGNA is the major is a representation of the neutron activation analysis, because in general, when we talk about the neutron activation analysis, is basically DGNA only. Until unless if there is a EPNA or that is epithermal neutron activation analysis or fast neutron activation analysis, they will clearly specify it. But if nothing is specified, it means that analysis is performed by using the DGNA only. And this activity found in the neutron activation analysis has been, counted by using this A activity is equal to N sigma phi and then multiplied by the 1 minus e raised to the minus lambda Ti and lambda E minus and lambda Tc. See this lambda Ti and Tc, this is basically Ti is for the irradiation times only, and this is once the activity has been formed. This is basically the loss of the activity due to the decay. So that's what is it. Tc is the cooling time is there. So here N is denoted the number of atoms in the target isotopes, where phi is the neutron flux that we have seen in most of the cases about 10 raised to 12, 13 neutrons per square centimeter per second. And sigma is the reaction cross sections. See, these are the, for each element, this is already, nuclear tables are there that will show you also. And from that tables, you can find out these reaction cross sections and depending on the elements. And then Ti is the radiation time, Tc is the cooling time, lambda is decay constant of the radioisotopes. And once this activity has been find it out, then you have to find out the counts per second. And how to get the counts per second from the activity? Once you multiply this number by this efficiency as well as the gamma abundance, because there are many, because as I told you, there are many gamma lines are there. So particularly, what are the abundance of that gamma abundance of that particular line? So those abundances also you will get from the nuclear data sheets. So by knowing this efficiency as well as the gamma abundance, one can know the counts per seconds. So these are the nuclear data sheets. So these are the various target species are there. So these are the isotopic abundance and thermal cross sections, sigma values, and these are epithermal cross sections. So if you are carrying out any kind of epithermal, so you need a sigma in the epithermal region only. And these are the activity produced. So T half, or this is the gamma energies, and these are the gamma abundance are there. So these are the two tables. With the help of these, like that, there are many, all the data sheets are existing. Whenever you are carrying out a neutron activation analysis, you have an access of these nuclear data, and you can use for finding this. So in case of this delayed gamma neutron activation analysis, or now we call as a neutron activation analysis, vast majority of elements that produce radioactive nuclide. This technique is flexible with respect to time such that the sensitivity for a long-lived radionuclide that suffer from interference by short-lived radionuclide can be improved. Because when you bring your sample and keep it for the decade, kept for a cooling time, see all this short-lived radioactivity. And I do not know because basically if you're aware about the radioactivity after say five half-life, we say that this almost the radionuclide is decayed. This is basically a thumb rule. Still some activity is there, but after having a five half-life, so for example, it's having a half-life of only 2 seconds only. So after say 10 seconds, that radionuclide will be no more going to give you major peaks in the gamma spectrum. So like that, after passing the five half-lives, their activity will be comes to a very minimum level at a very low levels, so that you whatever the interference are coming because of those lines will be avoided. Okay, so the selectivity, which is the key advantage of this neutron activation analysis over the other analytical methods. And then we are having both the instrumental as well as the radiochemical neutron activation analysis. So this we'll learn what is the difference. The instrumental neutron activation analysis basically it is generally possible to simultaneously measure more than 30 elements in in most sample type without any chemical processing. And whenever we are not doing any kind of sample processing or those things, basically the purely experimental neutron activation analysis. Okay, but there are certain cases. If we do once the irradiation has been done, there is some kind of a chemistry has been performed to remove the interferences. So this has been termed as a radiochemical neutron activation analysis. And basic aim is to just to to concentrate that particular radioisotope of interest, and then in the next PowerPoint we also see this CNAA. CNAA. See, if you avoid it because you know that these are the elements going to do the interference or they are going to hinder your neutron activation analysis. So you can do the chemistry even before irradiation also, so that you can selectively remove that particular matrix and take your only the element of interest and then do the neutron activation analysis. So that will be termed as a CNA. See, as like other technique, this also involve both the sampling, then pre-radiation sample treatment, such as that we call the sample processing. See, such as cleaning, drying, or etching pre-concentration of element of interest, or eliminating of interfering elements, and then subsampling and then packing. Irradiations can be the prompt gamma ray counting in case of PGNA. And then radiochemical separation only we do whenever we want to do any kind of a separation after doing the neutron activation analysis. And then we carry out these radioactivity measurements, elemental concentration calculations, and the critical evaluation result and the preparation of the neutron activation analysis report. That is the final report. Final report means we have to prepare the concentration and the uncertainty associated with that particular measurements are there. So this is how we are taken just one example. For example, you want to carry out the analysis of those trace element analysis in these particular samples. So you just collect the samples, and because your first step is that you just wash the samples actually, because washing is very necessary. Otherwise, there may be so many errors. The soil particles that will be attached with this leaves, and when you do the irradiation without even washing, then those element will also get irradiated and maybe contributing to the neutron activation analysis. The first step is that you wash the sample to remove all possible contaminant. And once you've done it, then the next step is that you have to take a very small sample out of it. So what you have to do, you have to completely dry it. The drying can be done by simply putting into the oven, or it can be done by the lyophilization also. So this is how you have to dehydrate. Basically, you have to dehydrate the samples. So dehydration can be done in any of these two methods. And then once the dehydration is completed, then you have to powder it, the sample, and then take a small amount of this powder samples and put in a polythene bag. See, this packing of the material of the sample is very crucial again this step and very essential also, because finally you are going to irradiate your the samples are there. And as I told you, this neutron activation analysis has been characterized as one of the uh, comes under the category of the comparative methods. So for this, you have a similarly matrix matching standards are there. So you must have a vegetation samples where the concentration of the different element, whatever your target analytes are there. So those analytes should be there, and you must know the exact concentration of that. So that samples. So this is how you have to collect the prepare a standard samples also, which you put along with the your sample actually. So both of these sample as well as your the standard matrix matching standard had been put in a some kind of a vials, and then this vials has been put into the by taking because the special system we call this rabbit system and work used by a bank at drive because basically say how it works is the rabbit system work much like the system used by banks at drive through windows. A canister carries item back and forth between the customer and the teller. Okay, so it will take put your samples in the system and then it will take the sample to the irradiation positions. And once the irradiation position is completed, you take it out and remove your samples from this thing. This is how you know it looks like, and it's completely a sterile technique is required actually for putting these things. And once your irradiation is completed, because you have to bring your sample, if you are not carrying out the prompt gamma neutron activation analysis, you are doing this BGNA. So you have to bring your sample back to the laboratory. So, but at this time when you do the irradiation, this samples gives a lot of gamma dose, a lot of gamma radiations are there. So basically for monitoring of this radiation level, there is always a health physicist is there. So this health physicist will monitor your sample, and if the dose from the your particular sample or the gamma radiation from your sample is more than the prescribed value, it will not allow. And then based on this gamma radiation also, there is a different kind of a lead canisters are there. So because which has been put on those lead canisters, and then it will brought into the lab where the counting has been done. And this, the measurement of the counting is done by using either a semiconductors. Basically, can be done by both sodium iodide and HPG or lanthanum bromide. But in generally neutron activation analysis, because we are doing the activation, there are many kind of gamma lines are existing. And if we are using any other like lanthanum bromide also or sodium iodide detector where resolutions is not that high, because in case of HPG detectors we are having resolutions about say 1.8 kV at a about say 1332 kV of cobalt 60. So that's why this resolution is very high. So we are using only this HPG detectors, and these HPG detectors associated with a complete electronics are there, that is spectroscopic system, and this spectroscopic system is used about MC high voltage unit and amplifier spectroscopic amplifiers are associated with it, and with this we do the counting and. As I told you, the most of this neutron activation analysis needed high purity detectors, and these are the neutron activation analysis. This is basically neutron instrumental neutron activation analysis, radiochemical neutron activation analysis, where we do the chemistry after doing the radiation. This is chemical neutron activation, where we do the chemistry before the activation, before the neutron activation analysis. And these are the advantages and disadvantages. Please ignore these down parts. And these are the instrumental neutron activation analysis, non-destructive, free from these are the advantages are there, and free from blank, region blank, fastened sample, because you are not added any kind of region, so it's free from region blank, fast and simple. And as we have given the example of a trace element in leaf. What are the disadvantages are there? There are matrix interferences are there, definitely there is a, because if you give samples, if you are analyzing the arsenic, lead or cadmium, there may be so many other elements are there. So the matrix interference are there, and high matrix activity also will be achieved because of those various elements are there. And then again this sample size, because we cannot use a large sample size. Then this already I spoken about this before irradiation, chemistry before irradiation and after irradiations. So these are the advantages of a radiochemical neutron activation analysis. Again, this is also free from a region blank and free from matrix interference due to matrix and other element, and we are getting a better detection limits. See, this is the best example of this neutron activation analysis. Going to give you is a very important tool for the in the forensic sciences. In the forensic sciences, they are regularly doing the variation in the concentration of lead and antimony in the gunshots. Because this the concentration of the lead and antimony in the gunshot will tell you whether the fire whether the shot has been fired from a long distance and a short distance actually. So these are the signatures are there, and the concentrations where the variation in the concentrations which can clearly indicate whether the fire has been whether the shot has been fired from a long distance or a short distance. And what are the disadvantages in this case of a radioactivation, radiochemical neutron activation analysis? That's again a handling of a high matrix activity, and again this sample size again here also is an issue. Similarly, for the chemical neutron activation analysis, where we do the chemistry before the doing the neutron activation analysis, high sample size, pre-concentration that we can do a very high sensitivity because you are doing the pre-concentration before doing the neutron activation analysis. Then similarly, you can minimize the matrix interference because you are taking out selectively your element of interest, and a low activity handling because in this case because you are avoiding much of the matrix, so that's why you are handling with the low activities are there. Then disadvantage is that because since we are doing the chemistry before doing the radiation, so there is this particular chemical neutron activation and this is not free from the region blank. Therefore, we have to be careful by minimization of a blank is essential in this particular case. What are the different kind of sources of error in neutron activation analysis? That is, the sample preparations, the contamination in inhomogeneity, and whatever the error you do in case of weight, because you have to take the exact amount of samples in that ampoules, whatever you are putting in a bag, so that if you can connect, if you done any kind of mistake in your weighing, that also lead to very erroneous results. Similarly, anomalous isotopic abundance and then neutron flux perturbation, because of any reason, if any neutron flux perturbation is there, that also causes errors. And interfering nuclear reactions are there. So these are the reactions which example of a nuclear reactions which interfere, and then spectral interference which comes into your gamma spectrum. So what are the limitation of these neutron activation analysis are there that definitely need a nuclear reactors. But as I told you, there are some cases we can take, but again, those things need permissions, actually, they need atomic energy regulatory permissions to keep those kind of a neutron source in your lab. Then very short-lived and very long-lived activation products, very difficult to analyze. And chemical species is not possible by doing this neutron activation analysis. And that is neutron activation analysis, for example, is not suitable for finding the light element like hydrogen, carbon. Well, see, basically, neutron activation analysis is possible only when you have a, because of the interaction, you can generate in a nuclear element which is should be radioactive one. so that you can do the determinations, gamma line determinations. So these are the, I already told you this basically highlights of a gamma spectrometry. So 1.19 kV at a 1332 of a cobalt 60. And then we have a efficiency. Basically, these are the HPG detector again has been classified based on their efficiency. And generally nowadays, even we are taking a well type and a 100% efficiency. So the detection limits are very, very high and good one. But again, their availability and their cost is of concern. Plus, they needed a good shielding because material they have to be when you do the determination of the radiant impact has to be it has to be whatever the contribution coming because of the background should be avoided. So that's why they need a very high shielding. Of course, good laboratory practice, like other kind of analysis here also, we need a good laboratory practices. So this is basically our lab where we do this. This is a high purity germanium. This is basically L-shaped germanium detector is there. So this is basically a place where we keep the sample. So it's a lead sheet. You just open this thing and keep your sample on these things. But again, there also you need a calibration. Actually, that's what we should see before doing this. It needs any calibrations, that need energy calibrations. Then you have to evaluate this full bit at half maximum calibration, that you have to see whatever the resolution is expected is coming. And then it needs an efficiency calibration. That efficiency means what is vary with the energy. So you have to do both the energy calibrations. Once you do the energy calibrations, so you can easily qualitative analysis can be performed. And once you do the efficiency calibration, then the quantification is possible. Okay. So at once you carry out the energy calibration, then you will come to know that this particular radionuclide is coming. For example, cobalt 60s are there. Cobalt 60s having 1173 and 1332. So once you have the energy calibration, then only you come to know that my peak is coming at that particular energies. So this is how we do this. We are using these standard sources for 152 europium, 226 radium, and 133 barium. So they are having many gamma lines are there. So these sources can be used both for the energy calibration as well as the for the finding the efficiency calibrations. So these are basically one example where we have used these 40 samples which has been taken, I think, from the Karnataka regions, and it has been irradiated. See here it has been irradiated and then it has been cooling, given a irradiated for 7 hours in the Apsara. See, this is our old Apsara where we having a neutron flux about say 10 raised to over 12 neutron per square centimeter per second. And after doing the 7 hour irradiations, it has been cooled for the 7.5 days actually. And then we have done this counting of a 24,160 seconds. So I think if you divide by say in 1 hour about this 60, so this how we do the gamma spectrum of this long-lived radionuclide which are associated within 40 samples are there. So one can find out that it contains samarium, europium, cerium, yttrium, lutetium, thorium, chromium, and hafnium. This bromide, arsenic. Okay, there's a gallium, scandium, rubidium. So these are how we can take. These are so many radionuclide elements are there in that particular 40 samples are there. So basically, these are the signatures which one can obtain see 40s of various regions having a different elemental compositions are there. So by doing the neutron activation analysis, one can pinpoint that whether this belongs to what regions. And there are three methods for the concentration evaluation for these calculations. That is called the absolute method. But once you do the absolute method, it's very difficult to find out the sigma and phi actually, because very tedious one. So we cannot provide a right input to the system, so that's why it's not in practice actually. So generally that we do it the relative method. Relative method means as I told you, that we take the, for example, if you are doing the analysis of this that cadmium, barium, and antimony in your samples, so you can take your sample as well as the standard containing these elements and then do the irradiations and then count the samples. So you will do the calculations in your sample of these elements based on the counts which is coming relative count which comes into your standard related to the standard actually. Then nowadays there is one more method which is used by nowadays by the people who are very professional in using this Neutron activation analysis. That is single comparator method. That's the term as the K0 method, which has been given a green signal by the International Atomic Energy Commissions that they can use these single comparator methods. So here in the single comparator method, they are using the, instead of multi-element standard, they are using the mono standard. So this mono standard can be of the gold, manganese, or scandium. So based on this K0, that's called a K0 methods, and then they do the final calculation. This is how we can evaluate the sensitivity in the neutron activation analysis. And this, as you've seen that this sensitivity depends both this isotopic abundance, neutron absorption cross-section, neutron flux, efficiency of the detector, gamma ray abundance, and delay correction factors, as well as the saturation factors. So these are the various, total elemental analysis amenable to elements which is amenable through this neutron activation analysis, so that you can see that more than 70 elements possible to do this neutron activation analysis. And whatever the red signals, you are getting it, that can be done by this prompt gamma neutron activation analysis, whereas what we call these colors. This can be done by the instrumental neutron activation analysis, and the blue one is by this fast neutron activation analysis. This is how various elements in the periodic tables covered in the different kind of neutron activation analysis. Similarly, the prompt gamma neutron activation analysis again can be, the red one, the detection limit about this 0.01 to 1 ppm, and yellow one is about 1 to 10, and green one is 10 to 100, and this light green is about 100 to 1000, and the black one is more than the 1000 ppms. And wherever the blanks is there, so there is no data which is existing in the literature so far. So the detection limit basically, as the other technique also, is ability, detection limit represents the ability of a given neutron activation analysis procedure to determine the minimum amount of elements reliably, and detection limit depend on the amount of the material to be irradiated and to be counted, neutron flux, the duration of the radiation time, and the total induced radioactivity that can be, and the duration of the counting time. The detector size, counting geometry, and the background. This is how these we can, in a various field, one can use the neutron activation analysis. So you can see that it can find the all type of sciences like biology, nuclear technology, forensic science, healthcare, geology, chemical sciences, material sciences, archaeology, and then environmental samples. So these are the certain examples. See, basically, this is a determination of arsenic in the hair samples. See, in general, the hair sample contains about 3.8 microgram per gram of the arsenic. But in case of Napoleon, it's a famous case where the Napoleon understood. There's apprehension that Napoleon has been dead because of the arsenic poisoning. So the analysis done on this hair of this Napoleon it shows that it contains about, say, 10 to the power minus 4 microgram per gram. So that's gives a boost to whatever the apprehension people are having that death is because of the arsenic poisoning. Similarly, if you, because this hair grow from the skull, and if you do this sectional analysis of the hair, one can indicate the approximate date of this arsenic poisoning also. Similarly, here this is one of the unknown sample we have received it, and then after doing this, of course, we have done earlier the DDXRF and the XRD pattern, and then it has been further scrutinized that this is radium only by carrying out the neutron activation analysis. These are already spoken this analysis of the gunshot, where we do this barium, antimony, and copper. So this will give you whether the gunshot has been fired from the long distance or the short distance. This is how the spectra looks like of the gunshot. This is from the HPG detectors. Similarly, always again this is used in the forensic science whether these two inks are same or not. So what we can do, we can just carry out the and gamma. We can use the neutron activation analysis and study their gamma spectrum. So by this we can just immediately tell whether these two ink which they are having the same origin or the different origin. Similarly, different kind of a geological sample where we have to find out the concentration of various element like manganese, arsenic, cerium, and rare earths. It can be easily given, in the red barrels or PG barrels or YG samples. This is again a gamma spectra of a clay sample acquired at a different time. See, basically here. See, this is a irradiation time of only 5 seconds, and then we are given a cooling time of about, say, 25 minutes. So this is how we got the different concentrations: the dysprosium, barium, titanium, manganese, magnesium, sodium, aluminum, vanadium, and so this is how we get the various different elements associated with this particular sample. But when we have a radiation time of about, say, 24 hours and a decay time of a 9 hours. As you can see that what more information you can get it. So this is how we can improve. See, this is both of these same spectrum. This is from 0 to 800 and this is from 800 to 1600 keV. So that's how we come. Versatility of this technique will be clear by this gamma spectrum of these clay samples. Similarly, this is, we got some sample from this regions, Uti Musky, which is supposed to be this particular area contain a precious metal like gold. So we have carried out the neutron activation analysis, and it will be further verified by using this charged particles neutron activation analysis. So this you can see that how results are very close actually. So they are very close, both of the instrumental neutron activation analysis as well as the radiochemical neutron activation analysis very close, and whereas the charged particle analysis also coming in this similar range. So with this, colleague, I thank you. And then again, if you have any kind of a queries, I will be very happy because if you ask me some question, definitely I will be very I can answer in a better way, and you can understand you can understand the intricacy of the particular technique. But for this, you have to ask me questions because I do not know what is going in your mind and what is your queries are there. So please come forward to ask me any query if you are having. Sajan, thank you. See, Sanjan, see, alpha error and beta errors, these are again, statistical term actually. If you are asking statistically. So this, I may not be in a position right now to answer this question of the alpha error and the beta error. Okay. And this alpha error and the beta errors, if you are asking technique to technique wise, or you are asking for which technique you are asking. Because first of all, I am not clear with your questions actually, where you are asking this alpha errors and a beta error. Detection limit of which instrumentation? Because definitely, as I told you, I am not the expert of the statistics. Sajan, Sajan, you can note down my extension. My extension is 22233. 22233. You can convey your message to Sabyasachi also, because first of all, I have to understand your questions actually. Sajan, please contact me on my extension 22233. Okay. Okay. Take. So with this, I do not know how many people you will going to opt for the exam. If you have any query, I think some assignment also will be given to you. If you have any queries, my email ID is with you people. So you can always welcome to raise any questions or any doubt to me. And if you share your mobile also during this your mail to me, then we can discuss one to one also. With this, thank you.